Okay, welcome to day 3. Today we're going to be talking about non-triangle based trigonometry. So the goal of this entire section is to move beyond triangles so that we're not restricted by acute angles anymore or even positive angles. So we'll be able to work with obtuse, angles bigger than 180, bigger than 360, just pretty much any angle we want. And we will be able to define the trig ratios in terms of trig functions of the real numbers. So it's kind of a big deal. You can read that note there. It just says we'll try to use radians as much as possible, but we'll also be thinking of them in terms of degrees just because it's a little easier to talk about sometimes. We'll start off with the basic definitions of an angle in terms of geometry and what we would call a trig, or a calculus-based angle. So in geometry you had two separate rays that together formed an angle in between. So this was one ray, so we'll call it ray 1, and this was another one, ray 2. And they had just this common vertex is where they both started from. In trig, or in calculus-based angles, we actually think of it as the same ray that's been rotated. So it starts on one side and rotates to the other. And we would call this the initial side, and where it stops rotating is called the terminal side. Okay, so this is the exact same ray. It'd be ray 1 and ray 1 if I were to label it. So it's a slight difference in the definition, and because it's not talking about the angle that's in between two rays, it's just how much we rotated it, we're allowed to deal with positive and negative angles now. Because if I rotate it the opposite way, it'll be a negative angle. So down here we have trig functions of real numbers. So here's where we're really going to formally define this. We have let t be any real number and let p of x be any point corresponding to t when the number line is wrapped under the unit circle with radius r. So right here I'm going to pause the video and let you watch this quick demonstration of what that looks like. That's fascinating, right? So cool. Alright, so in terms of what we're doing, I'm going to just put a point here, so we'll call this the point xy. Okay, this circle has a radius of r, and I can say that this is x over and y up, and here's a right triangle, so this still connects to what you're used to. Okay, and I have t would be the angle in terms of the circle, but it's also the distance that it's along that number line that it's wrapping around. Okay, so this little angle in here is where t would be. And so you can see I've already defined them over here in terms of this triangle. I have sine of t is the opposite, so y over r, cosine is x over r, and so on all the way through. Okay? And what this means is that if my point was down here, my x's and y's would both be negative values. Okay, so anytime that I used x or y, so in sine or cosine there'd be negative, in tangent the two negatives would end up canceling out. But it's kind of a cool little property, okay? So next it says, therefore, we have the number t and a number line always wraps to the point, and I should modify this. It should be r cosine t and r sine t. And that just comes from solving one of these two equations over here. So if I just multiply the r to the other side, there's y. So I can think of sine as a y value, and I can think of cosine as an x value. All right? That corresponds to right here. So since we can think of x and y in terms of r sine and r cosine, we actually don't need to use triangles anymore. And that's what lets us break free of triangles, is this wrapping of the number line. So since it's wrapping around a circle, we sometimes call trig functions circular. So we'll deal with that a little bit later. I'll give you a demonstration of what we mean. All right, so now we have this thing called coterminal angles. So coterminal angles are just going to be angles that have the same initial and terminal sides, but that their measures are actually different. So here I just have an example of a couple of them, just so that we can kind of draw them and see what I'm talking about. So if I have this first one, 90 degrees. So here is 90 degrees, okay? I start at the positive x-axis. I rotate counterclockwise 90 degrees. I can go 450 degrees. So that's going to be 360 and then an extra 90. So see, I started at the same place, the positive x value, and then I ended at the same line, the positive y value. Same exact thing happens if I do negative 270. So a negative angle starts here, but it goes backwards, so clockwise, and 270 will bring me all the way up to here. So all three of these angles in terms of trigonometry are identical because they all start and end at the same place. The exact same thing happens over here when we're in radians. I have pi radians is right here. 3 pi radians is just going to come around the circle. And then negative 99 pi, I'm not going to draw there, but it just goes a bunch around the circle 98.5 times, basically. Okay? So the type of questions I could ask you here would just be find and draw positive and negative angles that are coterminal. So I'll start off just by drawing the one that they give me. So here is 30 degrees. If I want to find an angle that is coterminal to this, easy way of doing it is just to add 360. So I'll go around the circle a full time past it. That's going to give me 390 degrees. Another way to do it is just use negative angles. So negative angles say that we go the opposite way. Simple enough, we just do 360 minus 30. Okay, so it's going to give me a negative 330. You should say it the other way around. You do 30 minus 360. Okay, so these are all coterminal to each other. 390, negative 330, and 30. So here I've drawn in the 150 and the 2 pi over 3. We're just going to figure out easy way of doing this. Okay, so we do 150 plus 360, and we do 150 minus 360. If I do that, that's going to give me negative 210 degrees and 510 degrees. It's my two answers. So that's just going around the circle a full time or going backwards until we hit it the first time. And we could keep going. We could just keep adding 360 or subtracting 360 over and over. If we're in radians, we have to take this angle and we need to add or subtract 2 pi. Now 2 pi is a little bit annoying to work with when we have a fraction, so I would actually write this as 6 pi over 3 so that I have the same base. And now I can just think of this 2 pi plus 6 pi, so that's going to be 8 pi over 3. And then I can do 2 pi minus, so that'll give me a negative 4 pi over 3. And that's just corresponding to those two different angles there. Straightforward, right? I don't know, you're going to answer a survey question right now and find out. So, all right, we have these things called quadrantal angles. So these are angles whose terminus sides lie along the coordinate axis. Okay? These things are tricky because they don't produce reference angles. So even if we wanted to use a triangle to try to figure this out, we couldn't. And so we have to rely on our definition that cosine of the angle is equal to the x value and sine of the angle is equal to the y value. And then tangent is going to be equal to the sine value divided by the cosine value. So what I need to do is just kind of figure out what's going on here. So I have negative 270. So I draw this first. I see negative 270, so I go clockwise 270. And I want to put a point here to work with. It could be any point that's on the positive y-axis. I'm going to choose the easiest one to work with, which is 0, 1. Now, I know sine is just a y value. Okay, so if sine is a y value, then I know that the answer to this is just 1, because that's the y value that I have right here. Now note, if I had changed this, and let's pick like a different one. Let's say I went up to 0, 2. This no longer has a radius of 1 if I were to connect this back to a circle. This would have a radius of 2. And my equation would have to change slightly because it's actually r cosine theta is what x is, and r sine theta is what y is. So I would have to actually take this and multiply it by 2 in order to figure out what was really going on with it. Okay? All right, do the same exact thing over here. I have tan 3 pi, so that's around the circle full time. It puts me over here. Again, I make a reference point to work with. I prefer to use one that's only one away. Tangent, I know, is equal to y divided by x. So in this point, I have 0 divided by negative 1. 0 divided by negative 1 is just 0. Here I have secant, so it's actually a little bit more annoying to work with secant. So I would think of it in terms of cosine, and cosine's an x value. So this is just 1 over x. So if I go to draw this, it's 11 pi over 2. Now I have really no idea what that is. So I'm going to just count it. So here's 1 pi over 2, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, 10 pi, 11 pi over 2 is right here. And again, first thing I do is put a little reference point. So my answer to this is going to be that it is 1 over 0, which is undefined. So secant of 11 pi over 2 is undefined. So here we get to why they're called circular functions. Okay, another name for that is periodic, and that's because they have a period, which means that they start to repeat themselves after a while. Okay, and that should make sense to you because they're coming from a circle, right? And so if we start right here and then travel this way along the circle, eventually we're going to connect back to where we started, and then we're just going to repeat ourselves. So in terms of sine and cosine, their period is 2 pi, which you might remember from last year, and tangent, its period is just pi. And we can use those to try to come up with some neat little things. Okay, so if you feel like you're good at this point, you can stop watching the video. I'm going to do just a couple more practice problems here. Just these 3 on this page. I guess it's really 6 because the first 3, but just as some practice. So you can stop watching now if you'd like. Alright, so if we're dealing with these angles right here, it's kind of a combination of using the fact that it's a period function and also that there's coterminal angles. So the first thing I want to do is try to break up this angle into some sort of multiple of 2 pi. So I'm going to do 57,800 over 2 pi and then plus pi over 2. And that's the exact same thing, right? Because they have the same denominator. If I were to add them, I would get 57,801. So this right here is a multiple of 2 pi. And since sine's period is 2 pi, I can actually say that, well, it just repeats itself. Every time I add a 2 pi to it, it's the exact same thing. It repeats itself. So this is identical to me just asking you what is sine of pi over 2. So where I want to know what sine of pi over 2 is, I draw it. So pi over 2 is right here. I put my reference point. Sine is a y value. So the y value for this point is 1. So sine of 57,801 divided by 2 pi is really just 1. I know, obnoxious. Same idea here. What I'm going to try to do is that there's 2 separate ones. I want to actually see if I can make a cosine of 280.45 pi, because then I could just subtract them and it would cancel everything out. So that's what I'm going to do with this first one. I'm going to break it up and say it's really cosine of 280.45 pi plus 8 pi minus the second cosine of 280. Well, this 8 pi says it just repeats itself. It goes around the circle 4 times, 2 pi each time. And so this is actually identical. So I really have cosine of 280.45 pi minus another cosine of 280.45 pi. No, let's just cancel each other out. I'm left with 0. Lastly, we have tangent. So tangent has a different period. It's any time that we add or subtract pi to it, it will be identical. And we'll deal with this when we do graphing more, so you can kind of see where these are coming from. But I have right here a multiple of pi. So this entire thing is actually equivalent to tangent of pi over 4. Okay, so pi over 4 is really 45. If you need to draw a triangle, you can. I would prefer that you not need to. But I have tangent of pi over 4 is just equal to 1. Okay, so here it says evaluate the trig functions, or the trig ratio, sorry, determined by a point in the first quadrant. Let theta be an acute angle in standard position, whose terminal side contains the point 5, 3. So standard position means that we're starting at 0, 0. It's going to go out to hit this point, wherever this point is, the point 5, 3. So if I view this, that's 5 and 3, and I can still draw a little triangle here. I can do my basic Pythagorean theorem and get that this side length is 34. But from here I can actually stop thinking about it in terms of the triangle, and I think about it in terms of x, y, and r. So I know that sine of my angle, theta, is going to be y over r. And cosine of theta is going to be x over r. And tangent is just a combination of sine and cosine. It's just y over x. And then I can do the exact same thing for their counterparts. They're just reciprocals. So using this triangle right here, I just look at it and say, okay, y value is 3, r value is the square root of 34. So this is 3 over the square root of 34. Cosine of theta, the x value is 5, so I have 5 over the square root of 34. Tangent's a combination of y and x, so it's going to be 3/5. Now for secant, cosecant, secant, and cotangent, I just take the answers I already got and I just do the reciprocal of them. So this is the square root of 34 over 3, square root of 34 over 5, and 5 over 3. Now this type of question gets more challenging if we're not in the first quadrant because our x or y values might be negative, so we'll have to be careful if that happens. Let's find the remaining 5 trig values, trig ratios, sorry, given that sine theta equals 3 over 7 and tangent is negative. Okay, so let's think back. We have our little all students take calculus. So if sine theta equals a positive 3/7, we know we're in either quadrant 1 or quadrant 2. If tangent's negative, we know we can't be in quadrant 1 because tangent's positive there. We could be in quadrant 2. We can't be in quadrant 3 because tangent's positive there, and tangent is again negative there. So we look at the overlap. So I know that this angle is actually in quadrant 2 somewhere because it's the only one where both sine is positive and tangent's negative. And now I can just do normal little math there. Okay, so I have my little triangle. It's sine, so I know that it's opposite over hypotenuse. I can use Pythagorean theorem, and I get down here the square root of 40. But pay attention to this. It's going in the negative direction because this is a negative x value in terms of the second quadrant. So when I go to figure out all of the rest of them, I already know sine, so I can skip that one. Whoopsies. You guys wanted to write with a thick marker, huh? Same exact thing that I just did before. So cosine is really x over r. So my x value in this case is negative square root of 40. And my r value is 7. Tangent is just going to be y over x. So my y value is 3. My x value is negative 40. And now I can just fill in the rest of them just by doing the reciprocal. Okay, so this part is easy. You don't really have to think about it. This is going to be 7/3 from what sine was. This is going to be 7 over a negative square root of 40. And this one is going to be a negative square root of 40 over 3. There you have it. That's the basics of working with non-triangle trig. You can see that we still are using triangles sometimes to help us out, but that we're trying to slowly move away and think of it more in terms of x, y, and r, and less in terms of the triangle. Okay? So, hope you liked it. Hope this wasn't too long. See you in class.